Hey everybody, in this video I want to code up a solution to the flower problem using Python. So navigate to where you created your environment using virtual environment or miniconda, and I'm going to type source and then series bin activate, and that will get me my environment. Okay, now in this video we're going to do some graphs, so let's install matplotlib. It's this cool graphing tool. We're going to graph the cost over time and see it go down. Hopefully we're ready. Let's open up our notebook. So we'll type Jupyter notebook, and we have to copy this because of some error with opening URLs. Okay, I'm going to make a new notebook. Now we're going to do some graphing. So if we want the graphs to show up in these cells, we have to do this crazy thing, matplotlib inline, and then we're going to import some stuff from matplotlib. So from matplotlib, import pyplot as plt, and then we're going to import numpy as np shorthand. Okay, so now that we've imported all we need, let's define our data. And so we'll say data equals. Now the data is going to consist of points or measurements, and each one is going to be a list itself. So it's going to be a list of lists. Okay, so there's the data from my own video. So I'm going to go back. And for the first one, it looks like we have a 3 and a 1.5, and it's red. So 3, 1.5, and red I'm going to say as 1. So each point is length, width, type, which is a 0 or 1 for blue or red. And I'll go ahead and add the rest here. Now the mystery flower, I'll actually give a name, and that had measurements 4.5 and 1, 4.5, 1, and we don't know what it is. So I just won't even put what our target is for it. We don't have any target value for it. Okay, that looks pretty good. So we have our data. So let me show you how to look at one of those. So we'll just say data 0, and that's going to give us the first item here. So these are 0-based indexing in Python. So 0 is the first item, and you can see it gives us another list. Let's look at the second item. So 2, 1, and 0. Because this is a list itself, we can get out the elements here as well using this indexing. So we put square brackets, and we can get the first item here with another 0. So we get 2. So if we wanted to say get this value of 1.5, we'd say 0, 1, 2 to get this list, and then 0, 1. And we get out that value, 1.5. So that's how we can access our data. Now we need our network. So let's remember our network architecture. It's very difficult. And we have one output. And this is the flower type, and our inputs are this first feature and then the second feature. So this is the length and width as inputs, and our two weights are W1 and W2, and we also have a bias that we add on. So let's get our weights first. So we'll say W1 is equal to numpy.random.randn. So randn gives us a random number from the normal distribution, and it has 0 mean and 1 variance. So we can take some samples by holding control and just running this over and over, and you can see we're getting some random numbers. They're going to be around 0, and they're negative and positive. So we'll make W1 a random number, we'll make W2 a random number, and we'll make B a random number. Right? Because the connections in our neural network start off random. So we'll initialize those and take a look at W1, let's say, and W2, and B. They're all random numbers. Now we're going to need an activation function, and for this problem, because of our flower type being only 0 or 1, Sigmoid is a good option, so we'll define sigmoid, and it takes a number in x, and it returns 1 over 1 plus exponential of x, negative x. Now let's try to plot this. So we can get a list of numbers in Python pretty easily. I'm going to call them t, and this will be the domain of our function, what we plug into this sigmoid. And so we'll say numpy.linspace, and we could say from -5 to 5 with 10 subdivisions. Now if I just print t out by typing it, you can see we go from -5, and then we're taking steps here all the way to 5. Now I can just get the output of this by running our list of numbers through my sigmoid function, and it will actually calculate whatever this result is for each element, and that will become whatever is in y. So you can see whatever's in y is all positive because sigmoid, remember, squashes all numbers to be between 0 and 1. Now we can actually plot this. So remember, we imported pyplot as plt from matplotlib, so we can say plt.plot, and then the x's are our t, and the y's are our y. I don't know why I use t here. You could use a big X. You could call this variable anything you want, but we can plot that, and there's our sigmoid function, which is pretty cool. Now you can see it's kind of like edgy here, not to be edgy, but we could up the resolution by making more subdivisions. So we could say 100 subdivisions, and now it's really smooth. And we could also increase the domain to see a little bit more of the squashing behavior of our sigmoid. So we go -20 to 20, let's say. You can see that numbers that are very negative get really squashed close to 0, and numbers that are really positive get very squashed close to 1. Now we're also going to need the derivative of sigmoid, so we can type that, sigmoid p. I use a p like prime, sigmoid prime, because sometimes you could say the derivative of a function f is f prime, like as a shorthand, so sigmoid prime. And that is just sigmoid of x times 1 minus sigmoid of x. It's kind of interesting how it's defined using the function itself again. It's kind of crazy. We could maybe see why that is in another video. But so that's our derivative of sigmoid, and we'll run that, and I could graph that by just running our domain through that. So we got our sigmoid curve in red and our derivative in blue, and let's make the domain a little tighter here. So if we look at the slope of the red line, let's start on the left. The slope is positive, and it's starting to get higher and higher and higher, and you can see that the blue line is really a graph of the slope of the red line. So right here the slope is at its maximum. You can see it's like the steepest part of the red curve, and that's why we have the highest part of this blue curve right here. And now you can see the slope is starting to decrease. Like the function isn't increasing as much as it was here as we move to the right more and more. And so you can see that the slope, is decreasing. Here it is. See how it's more shallow? It's less steep over here until it's almost flat. And that's why this is getting closer and closer to 0. The slope is decreasing over here. Okay, so now let's make our training loop. And what this is going to do is loop over our data, pick out a random point, run it through the network, see what it should have been, and that will become our cost. And then we're going to take the derivative of the cost with respect to the network's parameters, use that to update the parameters by subtracting it, and that will decrease the cost, improving the network's prediction for that point. And if we see enough points, we're going to get better and better predictions. So that's the idea. So let's try it out here. So we're going to run over our data thousands of times, so we need a loop. So we'll say for I in range, and we'll say 1 to 1,000. And let's just print I and see if that works. So this is going to run whatever we put in this indented part 1,000 times. Now why can't I just type 1,000? I can. Okay, let's do that. So we'll say for I in range 1,000. So this is going to have 1,000 times that it runs. It should go up to 999. Let's see. Yeah. Okay. So we want to run our code 1,000 times. Now we want a random index, so we'll say random index is equal to numpy.random.randint, and I'm hitting tab for that auto completion. And then we want the length of our data, and let's see what we get there. So we should be getting random integers that we can use to index into our data and pull out a point. So we could get a point is equal to data at a random index, and let's print out the point. And let's only do 100 for now, just so my screen doesn't go crazy. So there's a list of 100 random points from our data. So we see 2, 0.5, and 0. And if we look at our data, there it is. That's one of our data points, right? 2, 0.5, and 0. Let's make a scatter plot of our data first, actually, before we start to train, so we can kind of see if it looks correct. We're going to say scatter data for I in range length of the data. So this is going to give us an index that goes from 0 to the length of the data minus 1. We're going to get our point, which is equal to data at I. And then we're going to say plot.scatter. Scatter the point's first feature, the point's second feature, and let's just look at that first. Okay, we got all these points. Now we want them to be colored correctly based on their type. So we're going to make a color variable, and we're going to make it red by default, or just R by default. And we're going to say if point the type is equal to 0, color is equal to blue. And now we can just put C is equal to color, and there we go. Those are our points as a scatter plot. So we can see the flower at, well, let's change our axes a bit so we can see this better. Okay, that's better. So we added a grid, plt.grid, and plt.axis sets the x-min, x-max, y-min, y-max of our plot. So we see a scatter plot of our data. Okay, look at those points there. Blue, 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 like a T. Blue, 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 like a T. And red, 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 red here. That looks pretty good to me. So those are our points. Now let's do our training loop. So what our training loop's going to do is grab one of these points randomly, see what the network output is for it, and use that as part of getting the derivative of the cost, and bring that derivative back to our parameters and updating them to minimize the cost and get the prediction, more importantly, get the prediction of the network closer to what we want it to be at this point. So we're getting a random point. Now let's feed it through the neural network. So I'm going to make a variable called z, and this is going to be the weighted average of the point's features, so 0.0 times W1. The weighted average of the point's features and the bias, so 0.1 is the next feature times W2 plus B. So we can look at all these z's we're getting for each point, all these z's for each of these flowers. Now I'm going to make another variable called h, and that is the application of our activation function on z. So now we can print all these h's, and they should be between 0 and 1. So we're getting all these high values. Interesting. Now our cost is equal to the target, which is point, the third part of the point, right, with those zeros and ones we put. So that's our target. So the cost is equal to y minus t, or h, we called it in this case, minus t. It's really the network's output, the prediction. I should use pred because I use that in previous videos. So it's pred minus target squared. And the way we can do that is numpy dot square that. Okay, so that's our basic cost. The prediction minus the target squared is our basic cost. Now I can print that for each point. And we can see some points actually have really low cost, and I bet you they're red points because our outputs for h or our prediction were all really high, right? They're all close to 1, so all the red points are probably getting a low cost. Let's just prove that by printing our points information and the cost. So let's see, for these blue flowers, see the 0 here at the end? For these blue ones, they have a high cost, and for these red ones, they have a low cost. And that's because the predictions were all really high, just given the weights and the features right now. But anyways, it looks like it's working. Now we want to take the derivative of the cost with respect to each of our parameters. So we're going to have to work our way through the model and look to the previous video to see, why I'm doing that and how I'm doing that. First, we want the derivative of the cost with respect to the prediction, and that's the power rule. So really we have this minus this squared with a 2 out here. So we bring the 2 out in front, and then it's times whatever was in here, pred minus target. So we have the derivative of the cost with respect to the prediction, and so we're right here, and we want to take the derivative of the prediction with respect to z. So that's sigmoid prime. So this derivative of the prediction with respect to z is sigmoid prime evaluated at z. We're taking the derivative of this with respect to z. So it's the derivative of sigmoid, which is sigmoid prime, we defined over here, this blue function. And it matters where we were. If our activation was really high out here, the derivative is going to be really small. And if our activation is over here where the slope is high, the derivative is going to be high. So remember, it's evaluated at z. So now we're at z here, and we're going to go to w1, let's say. We're going to take the derivative with respect to w1. So we're going to say dz dw1 is equal to 0.0. Remember, whatever is multiplying w1 is the derivative of this. Now we can also, because we've worked our way through the graph here, right? So we can say dz dw2, let's do that next, and that's 0.1 because that's multiplying w2. And dz db, derivative of z with respect to b, is just 1 because we have a 1 times b here, you can picture. Okay, so we've kind of worked our way through our model, and now we can chain these things together. This is the chain rule after all, and get our derivatives of the cost with respect to each one of our parameters. So we'll say dcost dw1. Well, that's going to be the cost with respect to the prediction times the prediction with respect to z times z with respect to w1. And you can almost ignore all this middle stuff, and you see we get dcost dw1. But this is, of course you need all that, but just to check yourself, you can see, is this stuff matching up? Dcost dpred, then you should see pred, and then dz, and then you should see z. So whenever you see the end here, you should see at the beginning here. So we have our whole chain to get us from the cost to w1. We're going to do the cost with respect to w2. And that's going to be the same first part. We could store this somewhere. Let's do that. So that's going to be dcost dz. And we're bringing it through the pred. So we've got dcost dpred, dz. Now all we need is this in here. So dcost dz, dw1. Now we'll do dz dw2, and dcost db is dcost dz db. So those are our partial derivatives of the cost with respect to each of the parameters. Now we want to subtract a small fraction of them from our parameters. So we'll make a learning rate, make it a small number. We can tweak that later. And we'll say w1 is equal to w1 minus the learning rate times dcost dw1. And we'll do the same thing for the others. w2 dcost dw2, and b is equal to b dcost db. Let's print the cost as we go, but let's only print it if I mod 1000 is equal to 0. This gives us the remainder of the division of I over 1000. And so if the remainder is 0, I is evenly divisible by 1000. And so we'll get updates of our cost less frequently than 10,000 times. So I'm going to do 10,000 times. We should get 10 updates. Now, it doesn't really look like our cost is going down that much. So let's see why that is. Target. We have our target. Let's make our learning rate higher. Okay, that looks a little better. But it's kind of hard to see if this is really decreasing. You know, we want to see this decrease. And it's going to be a bit noisy because this is the cost for a single point, when really we care about the cost over all of our points. But first, let's just keep track. We'll say costs. Let's keep track of all the costs that we record, and I'm going to keep track of them all. Why not? So we're going to say costs.append the current cost, and now we can plot these at the end. So we can say plt.plot costs, and whoa, that does not look that good. It does not look like it's going down very much. So let's see what we're doing wrong here. Bump up the learning rate. I mean, that looks like it's doing something. You know, I'm not liking how it's not going down that much. I guess that's okay. Do 100,000. Alright, I mean, it looks like our cost is decreasing over these 100,000 iterations, which just seems like so much for this problem, but what are you going to do? We're ending up around here, 0.01. So our cost is pretty small. You know what, let's change these around, 0.2, go back to 10,000. Let's look at the cost for all of our data points as we update our parameters. Now we can append the cost for all of the points. Let's see, why is that so weird? It's a little weird. Oh, I know what's going on. We need to just reinitialize our weights every time we run. They're probably at some extreme values. So let's bring our weights down here. That's probably why. Okay. That's very strange. That's just weird. Let's do a really small learning rate. That's even crazier. Look a little more. That looks awful. Okay, after a lot of, well, not a lot, but a little bit of playing around, I went back to this JavaScript solution that I made, and I just used the same hyperparameters, they're called, stuff like the learning rate and number of iterations. And I'm getting the same parameters that we got here. So I'm going to use a learning rate of 0.2 and do 50,000 iterations. So 0.2 learning rate and 50,000 iterations. And every time I is equally divisible by 100, I'm going to get a little summary of the cost. So for each of the points, I run it through the network here and get out a prediction and see what it should have been, get the squared difference, and that goes into this cost sum variable. And then I just make that an average by dividing by the points that went into it. And I keep track of those, and if we look at the graph of those, you can see the cost decreasing here. And we still get these kind of spikes. And I have a feeling that these spikes of high cost are coming from points that are right here on this decision boundary. If you can see, in the JavaScript solution too, these points will still have high error. Like this red point, the prediction is 0.76. So you're going to get 1 minus 0.76, which is 0.24 squared, which is 0.05. And if we look over here, that's going to be one of these little guys here, 0.05. So we're down here. So it's all these tiny little spikes, right? These are caused by these points being so close to this decision boundary. Over here, our prediction is about 0.4. So we have 1 minus 0.4 squared, and that gets us, actually, sorry, the target for that is, we'll do 0.4 minus 0, so that's 0.16. So if we look over here, that's one of these spikes over here. So these spikes are caused by these on this decision boundary. And we could continue to push our parameters like crazy until the cost went down and down and down. But, if the prediction is lower than 0.5 for this point, I'm happy enough with that. And if it's more than 0.5 for this point, I'm happy with that. So let's plot all the, not plot, let's print all the predictions for each of the points. So for this point, which was a red flower, I call the flowers points and the points flowers, so bear with me on that. But for this flower, which was a red one, you see the target was 1. The model is saying 0.64, so it's above 0.5, so I would say that's good. For this one, it's blue, and the model is really, really low, so that's good. It really thinks it's a blue flower. For this one, it's a red flower, and it's really high, so that's good. Blue, low, red, high, blue, really low, and red, high, blue, low. Awesome. So for each of our points, it got it right. So now we can do the mystery point. So that's mystery flower. See, mystery point, mystery flower, same thing. We'll get the prediction for that and just type it here. And whoa, red. It's really high, close to 1. So our computer is telling us that this is red. Let's make a little thing here. OS. And we can do OS dot. What do we want to do? OS or sys? We want to run something on the terminal. OS.system. That's it. Thank God for Stack Overflow. We want to import OS so we can do some stuff with our operating system. And let's say hi.
Hi.
Let's try Samantha.
Hello, my name is Samantha. I am an American English voice.
Whoa. You're very loud.
Hello, my name is Samantha. I am an American English.
I'm an American English. Okay. We can make the computer say stuff now with this command. So let's make a function that's like which flower, and it takes the, what is it, length or width? Length and width. Width. And it makes a prediction, which is done right here. So we'll say Z takes the length here. W2 gets the width. B, the predictions here. Now we'll say if the prediction is less than 0.5, it's a blue flower. Say blue. Else, say red. So now we have our handy function here. Which flower? Let's say it's a 1-1. It's a weird shape of petal, but let's see.
Blue.
Oh, it's blue. Okay, let's work off of our data. So this is more fun. I know we already saw all the predictions, but let's just try this. 2-1. The flower 2-1. What is that?
Blue.
Ah, that's right. How about 4-1.5?
Red.
Whoa, that's pretty cool actually. 5.5 and 1. That's some good measurements.
Red.
Oh, it's red. Wow. Let's try the mystery flower. 4.5 and 1.
Red.
Wow, it's supposed to be red. Good job, computer. Good job. Let's try 2 and 0.5.
Blue.
What was that?
Blue.
That's right. What about the anti-flower? -1 and -1.
Blue.
Oh, the anti-flower is blue. How about -100, the mega anti-flower, the black hole, anti-black hole?
Blue.
Blue. Oh no. Oh, we got to stack. We got to not stack overflow, but a overflow because our input to the exponential was so huge. Interesting. So the mega anti-flower is giving us values in our computer's brain that are so small or so large that it can't store them. Let's try the mega flower.
Red.
Let's try the pi flower. Ooh, that's actually quite a mystery. Let's see if we could figure it out ourselves. The pi flower. Pi by pi. Oh, that's red. Pi flower is red.
Red.
How about the 90-degree flower?
Blue.
Oh, the 90-degree flower is blue. How about the E flower?
Blue.
Is that yeah, exponential. Okay. What about the infinity flower?
Red.
Oh, it's red. Holy moly. Oh, wow. What's the prediction
Red.
for the? Wow, it's 1. That's crazy. What's the weighted average of infinity times something?
Red.
Infinity? Oh, it's infinity. Okay. So the infinity flower is red. What other flowers? The 0 flower. The point flower.
Blue.
Oh, it's blue. Okay. All right, so our computer, you can see, has very interesting powers of telling us the types of flowers that could not possibly exist either in our universe. But anyways, this is how I would go about solving this by hand. In a later video, let's look at how to solve this with like TensorFlow or Keras or something that can spit out a model for us, and we don't have to worry about taking the derivative and training it ourselves. We can use all these fancy optimizers and momentum in our gradient and batch training, train on a couple of different flowers and then apply the update, all that good stuff. So anyways, well, let's look at that in a later video. But yeah, I just wanted to solve the problem using Python for completion for anybody who wants to use Python to solve it, and do it in a kind of interactive way here. So yeah, thanks for watching, and I'll see you guys in the next video, guys and gals.